Hello, today I'm looking at M3 International A-Level May 2015. This is question 5. So I have two fixed points A and B are 5 meters apart on a smooth horizontal floor. A particle P of mass 0.5 kilos is attached to one end of a light elastic string of natural length 2, modulus 20. The other end of that string is attached to A. A second light elastic string of natural length 1.2 modulus of elasticity 15 has one end attached to P and the other end attached to B. Initially P rests in equilibrium at the point O as shown in this figure, and I need to show that AO is 3 meters. So I will begin by drawing on the forces, or I'll draw on all of the lengths first and then we'll look at the forces afterwards. So basically in the part of the string that is AO, then I was told that the natural length was 2, and so I'll call this extension here X. Then the natural length of this part of the string was 1.2, and so here the natural length, the extension of this part of the string will be, I'll do 5 minus 2 minus 1.2, and that gives me 1.8. So this part of the string can be written as 1.8 minus x. Okay, so looking at the forces that are exerted on the particle, then to the left-hand side I'll have the force where I use the modulus of elasticity 20. So I'm doing the modulus divided by the natural length, and the natural length was 2, multiplied by the extension. The same thing here, I'll do the modulus, which is 15, divided by 1.2, and 1.2 is 6/5, and dividing by 6/5 is the same as multiplying by 5/6. And then I'll multiply it by the extension in this part of the string, and this is 1.8 minus x, and 1.8 is 9/5. Okay, sorry, I'll just put a 1 here. Okay, so because I know this is in equilibrium, I know that these two forces will equal each other. So here I get 20 divided by 2, so I get 10x equals, and here I end up with 15 times 5 over 6, which makes 25 over 2, multiplied by 9/5 minus x. Okay, so now to make a little bit of progress, I'll multiply this out. So here I end up with 10x. Here I've got 25 over 2 multiplied by 9 over 5, and that gives me 45 over 2 minus 25 over 2x. So I'll add 25 over 2x to both sides. If I think about how many halves this is 20 halves, so I've got 20 halves plus 25 halves makes 45 halves. And now I can divide both sides by 45 over 2, and so I'll end up with 1. So x is 1, and therefore the length AO is going to be the natural length, which was 2, plus x, which makes 3 meters as required. So that is the first part of the question for 4 marks. Part B. So now it says the particle is now pulled towards A and released from rest at point C, where ACB is in a straight line and OC is 1 meter. So basically this is pulled 1 meter this way. So at that point this string is not stretched because it's just its natural length, 2 meters, and this part of the string will be stretched. Okay, so show that while both strings are taut, P moves with simple harmonic motion. Okay, so to show simple harmonic motion, what I need to do is again consider the positions A, O, B, And I need to consider what happens when the particle is displaced a little bit from the equilibrium position, which is at O. So the equilibrium position is at O, and we know this is 2, this is 1, this is 1.2, and here the extension is 5 minus 1 minus 2 minus 1.2, and that gives us 0.8. Okay, so when the particle is displaced a little bit from here, and we were told it's displaced in this direction, so x is measured from here in this direction, then the particle is going to be here. And so now I need to again consider the forces on each side. So for this part of the string, I have the 10 times the extension, and the extension is going to be 1 minus x, where x is the amount it is displaced from the equilibrium position towards A. For this part of the string, I had, I think it was 25 over 2 was the modulus divided by the natural length, multiplied by the extension. So in this part of the string, I'm going to have 0.8, which is 4/5, plus x. And as x is measured in this direction, then I can write x double dot in the same direction. So now I can write down my equation for Newton's second law. So because x is measured in this direction, so is x double dot, then I have forces this way minus forces in the other direction equals the mass times the acceleration. So forces in this direction, 10 times 1 minus x. Subtract forces in the other direction, 25 over 2 multiplied by 4/5 plus x, is equal to the mass, which was 0.5, so a half, times the acceleration. Okay, so now multiplying out everything, here I end up with 10 minus 10x. Here 25 will cancel with the 5 to give me 5. 4 will cancel with 2 to give me 2. So 5 times 2 is 10. And then I'll have this times this, minus 25 over 2 multiplied by x. Okay, so to show simple harmonic motion, I'm trying to get x double dot as the subject. So now I need to simplify this and multiply everything by 2. So here I have 10 subtract 10, so these two parts disappear. I have negative 10 minus 25 over 2 x. So this is negative 20 halves. Subtract another 25 halves makes negative 45 halves. And so when I double that, I will just end up with negative 45. Okay, and I'm doubling to get rid of this. Okay, so therefore I've proved that this is simple harmonic motion because we have basically x double dot is negative omega squared x, and just for completeness I can say that omega is equal to the square root of 45. We can simplify the square root of 45 as well, and that will give you 3 root 5, just to write it in a little bit of a neater way. Okay, so that part of the question is another 4 marks. Then it says, find the speed of P at the instant when the string PB becomes slack. So PB, this part of the string here, will become slack when x is negative 0.8. So and at that point I'm looking for the speed. So I'll use the equation v squared equals omega squared bracket amplitude squared minus x squared, and omega I have here, so omega squared will give me 45. The amplitude, I can see the amplitude because the amplitude will be 1 because that is how much the string is originally extended. If you remember, it was pulled back here so that it was released from rest from point C, and OC is 1, so C is here, and so the amplitude will be 1 minus x squared, and this squared will give me negative 0.8 squared. Okay, so popping all of that into my calculator, I will get 45 open bracket 1 squared minus bracket negative 0.8 squared. Oops. And I end up with 81 over 5, and then I need to square root. So v squared is 81 over 5, so therefore v will be this square rooted, so 9 over root 5. Or if you want to work that out as a decimal, that will be 4.0 to 2 significant figures, or 4.02 to 3 significant figures. Okay, so that is part C. Then finally, I'm told that the particle first comes to rest, instantaneous rest, at point D. Find the distance dB. So B was that end point over here. I've just worked out the speed when it's here. And so what is going to happen? Well, once this string becomes slack, then the simple harmonic motion that was governing the motion up until now no longer stands. So that means I could either work out new values for the simple harmonic motion based only on one string and the speed that I know that it's going with here, or I could use energy to work out when is it next going to come to rest, because this string will continue to extend a little bit. So if you remember, it was moving this way with a speed of 4 in this moment, and so then it will take like a little distance for this to come to rest. So if I look at when PB becomes slack, then there is the kinetic energy that it's moving with, plus the elastic potential energy in the string AO, because at that point the other part of the string has become slack. Sorry, it's not AO, sorry, AP. And so then when it comes to rest, when the particle then comes to rest, then we know that this string will still be slack, and this string will be extended by 1 plus 0.8 plus a bit. So I'll have the elastic potential energy still in AP with extension 1.8 plus something. I'll call it x again, but I'll call it x dash because this is different to the x that I was writing about when I did this in previous parts of the equation. Okay, so the kinetic energy when PB comes to slack is half times the mass, and the mass was a half, multiplied by the velocity squared. Well, the velocity was this, so the velocity squared was 81 over 5. Plus the elastic potential energy at that point, so that was 10. No, sorry. So for the elastic potential energy, I'm using lambda x squared over 2L. That's my formula. So lambda was 20 times the extension squared over 2 times the natural length. The natural length was 2, so 2 times the natural length is 4. And then I need to multiply that by the extension at that point. And the extension at that point is 1.8 squared. And then the elastic potential energy for the string when it's extended more than that will be this, 1.8 plus x dash squared. Okay, so let's see what will cancel. So I've got divided by 4 here, here, and here. Then I can add all of that stuff up. So I've got 81 over 5 plus 20 times 1.8 squared. Okay, so I've got 81 altogether here, divided by 20. And so far I've got 81 over 20 is equal to 1.8 plus x dash all squared. So square rooting this. And then subtracting 1.8, I get x dash. And so I get 0.212. Now, what I actually want is the distance dB, and what I found out is the extension from here beyond that. So I need to do 1.2 minus x dash. So dB will be 1.2 minus x dash, and so I'll do 1.2 minus the answer, and that gives me this, which is 0.99 if I'm going to round it off to 2 significant figures, or 988. Okay, 988 if you round it to 3 significant figures. Okay, that last part of the question is worth 5 marks. I hope you found this solution helpful. Good luck with your studies.